So it's Masur-Veech volumes and intersection theory. And this is the geometric recursion seminar. So obviously this talk will provide a brief introduction on what are Masur-Veech volumes and maybe a little bit on why should you care, but mostly this will be about recursions or various forms of recursions that arise in that context and then compute Masur-Veech volume. So let's get started on the volumes. Guess everybody here is familiar with the moduli space of curves of genus G, Mg. And I think most people are comfortable with this, with the total space of the vector bundle over Mg, whose fibers are holomorphic one forms on the Riemann surface X, also known as flat surfaces. And if you want an example of such an object, so let's look, for example, at that kind of object, which is a polygon in the plane, and if you identify opposite sides, then you get a flat surface. That thing, star means minus the zero section, I don't want the zero differential, is stratified as a disjoint union over all partitions of 2G minus G of the strata, where mu is a tuple typically consisting of n entries, and mu is a partition of 2G minus 2. So in genus 2, the obvious examples are that one. If you look carefully, here the differential form, this is the surface of genus 2 with two simple zeros, one sitting here and one sitting here, and respectively at the other corners. And to give you a second example, for those who haven't seen that surface with, again, opposite sides identified, is a surface also in genus 2 in the upper strata. Okay. What is nice about those spaces of strata of flat surfaces is that they come with a nice coordinate system called period coordinates, and I need them in order to give you the definition of Masur-Veech volumes. So suppose you're on a little open set inside one of these strata, and suppose you define n to be 2G minus 1 plus the number of zeros, little n over there, then you can pick a basis alpha 1 up to alpha g, beta 1, and up to beta g of homology, that's absolute homology, and you add n minus 1 guys that account for the relative homology in n for n points. And if you integrate the holomorphic one form over all of these, you get a tuple, oops, so point x omega is being sent to that tuple, and that's an element in C to the n, so which gives local coordinates. So the fact this is local by holomorphism. So that gives you the coordinates on that manifold. Any other chart differs from that one by basically a symplectic base change, symplectic here, and integral coefficients on the absolute periods, an extension of the symplectic group with a linear group. So the upshot of that remark is that the integral lattice inside C to the n is independent of the choices, is independent of the chosen basis, and can be used to normalize the Lebesgue measure on on that space. Normalize the Lebesgue measure. By declaring out to the end that unit cube to have, say, volume 1. Normalized Lebesgue measure. Unfortunately, that measure has pretty obviously infinite measure on that space, because these flat surfaces, they have an area. This is just the flat area on the blackboard. The area given measured by the differential form omega, and you can rescale it arbitrarily, so no chance for that to have finite measure. But the area 1 hypersurface, this is the area 1 hypersurface. Those flat surfaces where the omega area has volume 1, that's a subset of real codimension 1 here. And for a little open subset here, maybe I should call that W, I can define the Masur-Veech volume of that thing to be, well, consider such an area 1 hypersurface like a hyperbola, and if you have a little open subset W in that hyperbola, you take the cone under that surface and measure its volume with respect to the full dimensional volume. So this is the volume, so the Masur-Veech volume of that set is to define the Lebesgue measure, that normalization of the cone in that sense under a dome. Okay, here's the definition of the Masur-Veech volume. So first of all, this is a volume form. I could write it down as a differential form for you if you would like to. And one of the important quantities is the Masur-Veech volume of just the stratum. I've just put mu to define this as the Masur-Veech volume of the whole space. I mean the whole stratum, omega 1 and g of mu, where mu as usual is a partition of this. So computing these things is compute these. Finiteness has been shown by Masur and Veech, and that's the question I'm going to address in today's talk, all of which is joint work with, what's the order? Dao Wei Chen, Adrien Sauvager, and Don Zaki. Okay. Maybe I'll tell you in a couple of minutes why one should compute these along after I've stated the first theorem. So one obvious way, which is somehow the very old way to compute such volumes, is to count lattice points, and I'll come back possibly at the very end of the talk to that. If you want to compute the volume of such a little cone, you count the lattice points in here. Well, lattice, this is not a very good drawing of a lattice. Count lattice points, and if you then refine the mesh size of the lattice, you will eventually approximate better and better the volume, so that gives you a way to compute that. Such lattice points will correspond to torus coverings, so you want to enumerate or count the number of torus coverings. Yes, this is an important way to formulate that in down-to-earth terms, and we might come back to that, and that gives a recursion and so forth. But in that talk, I will try to emphasize the new part, which is the intersection theory picture. In order to do, so second is intersection theory. If you do intersection theory, you should better have a compact algebraic variety hanging around, otherwise you're not going to get much information out of it. So what is the compact algebraic variety? Well, That space, that stratum, is non-compact for two reasons. First of all, you can rescale, and as an algebraic geometer, I certainly don't want to go to volume, to real hypersurfaces. The way out is to projectivize. Projectivize, you go to P omega mg, which is surfaces up to complex rescaling. Okay, that space is still not compact, because, as you all know, the moduli space of curves is not compact either. There's the linear Mumford compactification, which is very nice, and adding stable curves, and that's almost what we're going to do here as well. The problem is, just going well to the linear Mumford compactification, you're losing way too much information. On the other hand, if you have the type differential gives you n marked points. So you have here a natural map to omega mgn from that point. Just record where are the zeros. Okay, maybe I should say that from now on, I should say that zeros are labeled, which prevents me from taking here unnumbered stuff all the time, and it's an easy factorial back and forth between the two volumes. So let's have zeros labeled all the time. You could also, over mgn, that's something we can easily compactify. So if we write bar, here this is the linear Mumford compactification. And over that, you still have the, well, total space of the relative dualizing sheaf. The Hodge bundles, in some sense, extends perfectly to stable differentials over omega mgn. And so you can embed that space in here and take its closure. Which is a space that is moderately useful. So I take this, so I denote with IBC of mu the closure of the image in here. Closure of.
Projectivize the second factor.
I should projectivize here as well, thank you. Closure of the image. Why is that thing called IBC, like incidence variety compactification? Well, that space is way too big, because in that space you can let those endpoints float independently of the g-dimensional space worth of differential forms. And even in the interior, if the curve is smooth, this space is way too big, unless you impose that the zeros of the differential form are precisely the endpoints. They are incident. That's why we call that thing incident variety compactification. Okay, I'm almost ready to state the theorem. Maybe not yet. One more step of preparation. So on mg and mg bar, we all think are very well aware of the usual characteristic classes. There is lambda k, the kth Chern class of the Hodge bundle. There is the on mgn. There is the psi classes attached to the marked points, and there is of course the boundary divisors. Delta 0, or delta irreducible, I should say, the irreducible boundary divisors, delta 1 up to delta g over 2. These are the divisors downstairs, and since this is just a vector bundle or a projectivized bundle over there, the intersection ring of that total space is not much more complicated than that one. There is one more class, which is the tautological class on P omega mgn bar. There's one more class, namely the tautological class of that projectivized bundle, and of course the pullbacks of all these classes. And they generate, totally general statement about any projective bundle, they generate, if I take generators here and O of 1, I can generate the Picard. So that bundle, this is the, which I want to abbreviate by psi, is the tautological bundle. And that tautological bundle satisfies a relation. The gth power of that bundle can be expressed in lower degree polynomial. I'll need that later. Okay, now I really have all the pieces together to state the theorem, which says that the Masur-Veech volumes of the strata are intersection numbers. Namely, let me introduce a class beta I, which is the product of psi to the 2g minus 2 and the psi classes for I from 2 to n. And for convenience, I'll include a normalizing factor here, mi plus 1. You'll see in a minute why it's there. So this is a cohomology class. This is a curved class. Curved class on the compact line strata. And the theorem.
Sorry, there's two different I's, right?
Thank you. There's two different I's. That J runs from. Okay. This J is from 1 to n. J different from I. And this is J, and this is I. Yes. Thanks. Namely, Masur-Veech volume can be given in two, not obviously two ways as an intersection number that are not obviously the same. Namely, on one hand side, I intersect the beta I with just one more power of psi. Or the second version is that I take psi to the 2g minus 2 and add the missing psi class. So I get here 1 to n psi. Let's put here j as well. And the two things, there's a little normalization. A pi power is hanging around, and a factorial, 2g minus 3 plus n factorial. And here, it's almost the same prefactor, except for 1 minus sign. So why is this thing sort of morally the correct statement? That statement has sort of a lot to do with the form of the period coordinates. So let's take the version that I is equal to 1, then I have really j's running from 2 to n. So that sort of measures the relative periods. I mean, this is for each point, but the first one you get some relative period that is being measured, and that measures sort of the absolute periods. This is a moral statement. I can't make any literal sense out of that. So one could try to prove that theorem by representing the Chern classes of these bundles with appropriate two forms, and so that when you wedge them together, you get the two form that is implicitly behind the period coordinates there. That's one possible strategy of trying to prove that, partially due to boundary issues and other issues. We are not able to do that. So we'll take a different route to prove that theorem that I maybe want to call.
So the lambda classes do not play any role?
The lambda classes do not play any role here. They enter in the proof. And this is, of course, the integral over the IABC of mu, because mu should appear on the right-hand side. And okay, maybe just for the name, why is that thing good? Okay, why is the second thing good? The second thing is totally symmetric in all the variables. So the second thing is tells you that after having included that little normalization factor, it doesn't depend on I. That's the content of that second statement. Why is that called beta? Yes. So this is the advertisement of why that theorem is maybe interesting. So there's a paper by Kontsevich which goes back to '96, and by now, in 23 years almost all of the statements in that paper, which has I don't know, has produced some 500 pages of subsequent work, if not more. Almost all statements have been proven. We tick one more on the list. Namely, that paper is on Lyapunov exponents for those spaces. I don't want to get into the details of defining Lyapunov exponent on the space. Either you know or you can ignore that remark. And in case some of these Lyapunov exponents was expressed there as a ratio of a certain class beta, and here with what I should call psi in the notation that I have here, and with a class delta naught, a class delta naught, a delta irreducible, the irreducible boundary in class. No, sorry, why do I put a sum sign here? Sorry, just integral intersection product.
I know that Kontsevich called the lambda I, of course not the lambda I you have.
No. That's. I think this is pretty consistent with what I what I had there. So there's certain classes beta, and Kontsevich in that paper says we almost constructed the toroidal compactification of the moduli space to justify that. I mean, almost took another 23 years. So beta is called beta because it's beta. And to link that with the sum of Lyapunov exponents, for those who know, sum of Lyapunov exponents up to the direct term is basically area Siegel-Veech constant, and that's the volume, and that's the second theorem in the paper. I'm just talking about that expression computes area Siegel-Veech constants, but I won't be able to say more about them in that talk. Yeah, so I'll leave it with that comment. Area Siegel-Veech constant is one thing. So another application is just saddle connection. Siegel-Veech constants.
So the remark was that you give another proof of this, or you don't consider it a proof what Kontsevich is.
No, Kontsevich is not. Kontsevich is a research announcement. One of the greatest research announcements I ever read, but it's a research announcement.
The following section is called proof.
Yes, thank you. Add the 120-page paper by Eskin, Kontsevich, Zorich, which provides an intermediate step, and then add that paper, and then I call it a proof. Saddle connection, Siegel-Veech constants. So what's a saddle connection, Siegel-Veech constant? A saddle connection is a geodesic between two singularities. Suppose, so you want to measure the growth rate of those, the number of those saddle connections. Very roughly, you might think the following. Suppose you're standing at a singularity. Let me get back to the singularity. So here's the singularity, and then that singularity counted that has the angle 4 pi around it. Go around it and you'll check. And that singularity has also the angle 4 pi around it. And the number of saddle connections that you can find joining them, well, naive thought, it might be proportional to the total angle around. So here, this is the same point as this, and this has an angle of 6 pi around it. And of course, the formula should be somehow be symmetric. And I think the whole community was a little bit biased by the fact that Anton Zorich, Alex Jeda-Fatreya, and Alex Eskin have a paper saying that for quadratic differentials, half translation surface is not proportional. And so that so the application is, yes, if you do a slight correction by counting them by homology classes, you get the proportionality. So the saddle connection Siegel-Veech constant was counting saddle connections, say from the first to the second singularity, is not only proportional to the angle, it's very simply proportional. It's just the product of the angles. Well, your pick if there's a pi. I mean, I haven't said how I exactly normalize these things. The pi, that makes the pi gone. And the third application of that procedure is, maybe I should state that after the next theorem, because you'll see it much better with a recursion in the picture, is namely that that theorem plus its friends for connected components little remark and third of the paper. These strata are not connected. Connected components are classified by spin structure and hyperelliptic, and sometimes there's hyperelliptic components. So there's a similar theorem for each component separately. So that's why I say that the theorem plus friends for connected components implies all large genus asymptotics. The genus asymptotics. So this was basically all of them were conjectured by Eskin and Zorich, and I certainly shouldn't mention that Amal Agarwal has proven a very interesting, very substantial case of that by a very direct method, not including, say, connected components and giving a much coarser estimate. Yeah, sure. We have Siegel-Veech and the rest is, yes. Okay. So let me state theorem 2, which now finally goes to the topic of the seminar, recursions. Okay. So I'm giving you a pretty good recipe to actually compute these things, which is not directly obvious that, well, you have to know how to work on the IVC with the intersection numbers in order to deduce that, to pass between theorem 1 and theorem 2. Namely, okay, let's take first the base case. The base case meaning all those strata where you have a single zero of order 2g minus 2. So in that case, I'm defining a generating function, the generating function A. Sorry, let me pass to a slight renormalization. I don't want to move or drag around these factors all the time, so I'm declaring this intersection number, just AI of mu. Yes? So I don't no longer want to compute volumes, I want to compute AIs, and obviously the difference is very different. Okay, I'm taking the generating function of the AI of 2g minus 2. Well, there is only if there's only one zero, there's only a1, so I can, well, either put it or not. With a little prefactor built in, and I'm putting t to the 2g, t to the 2g minus 1, and 1 over t. And I'm defining b of t. It's just the expansion of z over t over sinh t.
Sorry, what are you summing over?
G greater or equal to. This is basically the generating series of the volumes of the principal strata, plural. And for later use, let me give the coefficients of that expansion the name bj t to the j greater or equal to 0. These are almost Bernoulli numbers, so up to a little rescaling. So then the theorem states that bj is the constant coefficient of a of t raised to the jth power.
T to the j or t to the 2j in b of t?
Say it again?
Because b of t is even.
B of t is even, yeah, the odd ones are 0. And here you also get the odd ones are 0. Well, this is determines the a's by solving a triangular system of equations. You can rewrite that equivalently using the Lagrange inversion. That a of t is 1 over q inverse of t. That 1 over is divide power series, and that's functional inverse, where q of u is u times exponential running maybe out of space, some k I minus 1 factorial bk u to the k. So these are the bk's, of course, that appear here, and that's k greater or equal to 1. Okay. That's also proven, well, there's two proofs of that. One by Sauvaget, completely using intersection theory. We give a second proof that is unconditional on improving the compactification using recursions, but I don't want to get too much into that. I want to emphasize on the second part of that theorem, which is the recursion formula. Namely, if I want to compute A of M1 up to Mn, so the volume of the stratum mu with entries M1 to Mn, I can pick any two zeros and can make a sort of a focus, this recursion focus on two of them, say, let's say the first two, so I multiply them by the first two, and then I get a sum. Okay. The main term that you should keep in mind is that I get the sum over always over k greater or equal to 1. And I get the product of k volumes. So I take that this is mu, and I partition mu as the direct sum of mu I. I is 1 to k. Okay, I'm partitioning my sets of zeros, and I roughly get the product of A of mu I. I from 1 to k.
Sorry, what is A? Before it was AI, so there was a...
Oh yeah, this is, before it was AI, but in passing I also said that it doesn't depend on I because of the second formula. So you could put either A here, put A1 here. Well, if you want to be picky and give a clean proof here, I would put A1 here. If I'm telling you this as a theorem, as a final result, it doesn't depend on the index anymore. Same remark here. You should put one of the indices that appears here. Okay, so the very rough structure is, you should partition into any number k of ways your index set, possibly empty, and you take the product of the preceding volumes. There will be a bit of decoration coming up, but before I fill in the decoration, let me a little bit elaborate on the structure of that recursion.
So what do you mean by empty partition?
Some of those mu i's could be empty. You'll see them in. You'll see absolutely them in. Think of stable curves. Think of stable curves with a bunch of points, and forget the fact that we have differentials here floating around. So we're focusing on two special zeros, and we let them approach. So we're bubbling off a special component. So the geometric picture is we're bubbling off a special component that carries the first two zeros, 0, 1 and 0, number 2.
So there's a node point. So where does the node appear?
There's the two bubble off, and so if they bubble off, they sit on an extra blown up P1 component, but there may be many components that meet that component. It's not necessarily only one.
You bubble over P1 and you think about the P1 being decorated with 2.
I'm thinking of the decorated with 2. So there's 3 pictures I might draw. This is the schematic real picture. The real geometers might like, here's a P1, and to make it here on the front of that P1 I put Z1, on the back of that P1 I put Z2, and like an orange, before peeling an orange, I slice it with 3 slices. Yes, now we're ready to peel the orange. And there's 3 components hanging around. In that case, whatever genus you like, they are connected to that special P1 that's inside here. So if they're connected to that special P1, I'm drawing that schematically. Well, you should think of a color connecting each of those slices that you get when peeling the orange to one of them. For those, this is hyperbolic. This is the hyperbolic picture. And if you want to just simply dual graphs, where the components are represented by just a point, there's one central component, which is the P1, and then there is a bunch of other components over here.
Which are all different from P1, right?
Not necessarily. They could be P1 as well, so let's include that case. But in that case, for the thing to be stable, you have to have a bunch of mark points here. So let's put, say, Z1 and Z2 are the mark points that are sitting here. The last component is, let's say, I put Z3, Z4 here, no marking here, to give to explain that empty thing here, and there's 2 sitting here. Okay, Z5 and Z6. Z5, Z6, Z3, Z4, Z3, Z4, Z1, Z6. Okay, this is 3 pictures, depending on which way you like to see stable curves. They're all basically equivalent. Okay. So let me now try to complete what is actually going on here. So you might wonder what happens to the if you degenerate to such a point that should be a boundary point of the IDC. You might wonder what happens to the differential form. Well, on each of those differential forms, you will get a restricted differential form omega on the first component, omega 1, maybe omega 2, omega 3. And if you now count zeros and poles, you might wonder, what does that component actually, well, this is pre-limit, this is a color, but at the limit, this is just a marked point, and we have a node here. What's the order of zero and pole of that limiting differential form at these points? That's part of the structure that we, Bainbridge, Lauet-Chen, Semprogevsky, Quentin, Gendron, have determined when computing how does the boundary of the IBC look like. Boundary points of that compactification correspond to differentials omega that have a zero here and a pole here. And the order of zero here that I want to call by P1 minus 1, well, order of zero here and order of pole here add up to -2. That should be familiar. You should be familiar with that in the case of the Linie-Mumford compactification, where -1 plus -1 adds up to -2. That's what you require for a stable differential. But in that case, because of the fact that when you go towards the boundary, the differential form vanishes to higher order on those on some components. That after rescaling, you'll be led to the fact that you actually have zeros and poles, where you just have the fact that they add up to -2, but no longer they have to be both -1. If you have never heard of that, just take it as granted that this is the structure of a boundary point here. So here, the differential form omega will have a zero of order P1 minus 1, and here, this will have a pole of order, well, pole order is minus P1 minus 1. Local picture of such a thing is, well, this is a singularity with P1 prongs. That's a local that's a local structure. A differential with a zero of order P1 minus 1 has P1 outgoing real axis. So it looks like that for P1 is equal to 3. And that's the same thing at the opposite end, at the end of infinity for a pole. So that's why you can glue these things together. Okay, same picture here. You have a P2 here and a P3 here, and we're getting there. So as you can guess, that component here has to be of what type? Well, omega 1 still vanishes to the order M3 at Z3. It vanishes to the order M4 at Z4 on that component, but it also has to vanish to that order on that point. So that's why there's a blank here. So we'll have P1 minus 1. The order of 0 is P1 minus 1 here, and I'm summing over all possibilities of P1.
Sorry, I'm slightly confused. Are you saying that you put all the poles on the P1 and then
Yes.
and then you get many poles?
Yeah. No. It's just okay. I put all the poles. There's not that many possibilities. Okay. Let's write down an obvious equation, namely that the sum of the poles here, and the poles are of order P1 minus 1. That's the pole terms here, plus M1 plus 1 plus M1 plus M2 plus 2. This is the order 0.
Two zeros are
Oh, no, sorry, the 2 goes to the other side. Is equal to negative 2, because this is a differential. So that's an obvious constraint that comes in a minute. Okay.
So by the concept way now, you just pick you fix two zeros and then you do all the sort of bubbling that puts
Yes.
the M1 and the M2.
Yes, I'm fixing on 2 zeros and I'm doing all that that is admissible from the bubbling with these 2 zeros fixed, and you'll see that constraint automatically comes into the picture. So what is happening actually here? On the P1. So on the P1. On that P1 we also have, well, the differential form degenerates also to a differential form here. Actually the differential form is 0 if you approach the boundary. But you might rescale just by the order of magnitude. It goes to 0. Rescale it so that you get something non-zero at the limit. What do you get non-zero? Something non-zero at the limit. As we discussed just with Ursula, that thing has zeros of order M1 here and M2 here because that was prescribed all the time. That has poles here. I mean, I ask you to believe me on faith. These pole orders, they are arbitrary. And it's a P1, so that some condition holds. And now comes one more very important fact, the global residue condition on the incidence variety compactification. The differentials are, well, that you should have on the various components of such a boundary stratum are pretty much arbitrary given the prescribed vanishing conditions, but there is one global residue condition that you have. Namely, whenever you take something, a level passage, I mean, difference between two levels, and whenever you pick a component on one level, the sum of the residues that goes in is 0. Well, that sum is a one-term sum, so the residue is 0. So that differential has residue 0 here, it has residue 0 here, it has residue 0 here. But that's great. So differential on that component with just 0 residues is an exact differential. So let me call that differential down here omega minus 1, because it sits on the lower level, on the minus 1 level, implies all residues of omega minus 1 are 0. That in turn implies that the differential form is exact, that omega minus 1 is d of f for some function f that goes from that P1, that's the P1 on lower level, to just P1, it's a meromorphic function. That means that this lower level object naturally has a structure of a Hurwitz space. This means lower level is naturally Hurwitz space. The Hurwitz space of P1 covers. And the Hurwitz space of P1 covers of a very special type, namely of type, well, let me do the general case because I will, I don't know if we'll get there. I might need. So there's 2 points that are independent, and there's the whole string of poles that go to 1 point. And in general, it's a Hurwitz space of type M1 plus 1. Then I have M2 plus 1, and I could do even more of them. Well, if I want to generalize, which would happen if I come to the proof. Let's see. MR plus 1 is an independent number. And here you should think mostly, here still, we're basically stuck to the case R equals 2. And then here you put all, the last partition is all what you have at infinity. At infinity, it's the poles give the ramification order. It's P1 up to P K. So this is a Hurwitz space of R plus 1 point covers. R plus 1 of covers with R plus 1 branch points. So part of that structure up there is the Hurwitz number. So the Hurwitz number for covers with one point with that branching profile, a second point with that branching profile, and a third point with such a multiple branching profile is not so hard to compute. You take the product I equals 1 to k, x to the pi minus y to the pi over x minus y, also factor that, x, y, and now you take the coefficient of x to the m1 plus 1, y to the m2 plus 1. Maybe let me put that behind, oops, each factor. Yeah, I think it's each factor, it's good like that. In particular, you will see that this number is automatically, this is homogeneous, that polynomial. That number is automatically 0 unless that condition is satisfied. So if I tell you now that this Hurwitz number, P1 of M1 plus 1, M2 plus 1, and underline P is the tuple of Pi, sits in here, then that constraint is automatically taken care of. Well, there's a bunch of cyclic, bunch of things that's almost correct. Here I put a k minus 1 factorial, which comes from cyclically ordering on that P1 the k branches. And here, because I numbered the parts of the partition, I should divide by k factorial. I could have divided by k if I like. And there's a few other minor terms which are still off. Namely, here there is a 2g j minus 1 plus n of mu j, and a factor of pj that still have to be added here. This is gj, this is the genus of the jth component. Note that 2gj minus 1 minus the number of points in mu, minus the total weight of mu I is equal to pj. This is Gauss-Bonnet for the jth component.
So where does the factor come from? Why does it arise?
It comes from a global normalization where you have those multiplicities hanging around here as well. And if you take an even more symmetric way is multiply the left-hand side by all mi's plus 1. And then here on the right-hand side, you will see, and here you multiply also everything by its ingredient plus 1. Then this ingredient plus 1 stays. The first and the second also stay. And the third to the last, you can divide them here and you can divide them here. That's the more symmetric version where you really see where they come from. Okay. So what did I do now? I told you the formula. What will I still manage to do in the last 5 to maybe a bit more minutes, is tell you a little bit on how to prove that theorem 1 is equivalent to theorem 2. Proving neither of them. We don't have a direct proof of neither one nor the other. Maybe I should emphasize one more thing why this recursion is good or useful.
You get the quasi-modularity statement?
That's a long story from there. I have to set up all the other end of the recursion. The proof goes via that, but I can't do that here. So why is that recursion sort of good? So among the terms, among the terms on the right-hand side is the case k is equal to 1. And that case k equal to 1, I can graphically indicate it. So there's the lower order component, and there's 0, z1, and z2. And on the upper level component, I of course have, where else should they go, z3 until zn. And since here I have a pole of order minus z1, minus z2, minus 2, because this is a p1, I need here a 0 of order z1 plus z2. Aha. That shouldn't be so surprising, because if you think of collapsing recursions, one of the terms comes when the two zeros actually come together. So that's that term.
You mean m's, right? Orders. You wrote c's. That's
The c. Yes, thank you. So the orders is m's, m, yes. And the points are called z. So in particular, this means that in that recursion, and I tell you that this factor is just 1 for that recursion. Roughly, this tells you that the volume of m1, m2, ... is less or equal to the volume of m1 plus m2, m3, ... Don't take that totally literally, because you have to take care of the norm. I threw away the normalizing constants that are floating around, but they're not bad, and that's the thing that gives you the asymptotics. So for all asymptotic properties, we do it for the minimal stratum and for the principal stratum, and the factors here in front are just good, so that everything in between is squeezed in between the two extremal cases.
What kind of asymptotics?
Large genus.
And fixed partition?
Oh no, completely arbitrary partition. That's cool. It's uniform in the partition. It's up to.
Yeah, but fixed. Or not?
No. Oh, okay.
Sorry, there is z and there is mu.
You're right. Let me give you the precise statement in that direction. Namely, for example, the volume of so if I take the volume of the stratum U and I just multiply it by the m1 plus 1s, that's the only thing that I need to normalize. Then this tends. This is for large for g going to infinity, just 4 plus O of 1 over g. For all uniformly for all mu, which are partitions of 2g minus 2. Partitions of 2g minus 2. And we can. This is basically what Amal Agarwal also did, and we can do much more precise. For example, this is equal to 3 minus the sum of the mi plus 1 plus where's the g gone? Oh yeah, this is roughly g. So plus O of 1 over g squared. That's
Sorry, so you get it different?
no, just a more precise. This is the second order, the subleading term.
Where the g?
The g is the sum of the mi plus 1.
Sorry.
Okay. So strategy for the equivalence between theorem 1 and theorem 2. So one of the starting points in that direction was the thesis of Adrien, who computed the class of the incidence variety compactification in terms of generators, well, in the topological ring of MGN bar. Said like that, that's a little bit more optimistic than his statement actually reads, because his statement is a very complicated recursive formula. Because he does something, there's a principal term and there's a lot of boundary term that you have to subtract. So what the cool upshot is that of that paper and maybe some subsequent papers is that if you want to actually do computations, things are much better than his complicated recursion seems to look like. And that's here I'm giving you one instance of what that does. So what is one of his main statements is that the psi class is pretty closely related to the psi I class multiplied by mi plus 1 in the sense that there is a control sum over boundary classes. So alpha is the boundary class, and what is a boundary stratum? How do you describe a boundary stratum? Well, boundary stratum for MGN, you're used to the fact that they are given by dual graphs. Here, additionally, boundary strata are given by a level function. The level function, tells you which vertex sits at which level, at which different of the components the differential form stays of positive volume, where it goes to, where does the volume go to 0, and maybe even where does it go to, its volume go to 0 even more quickly. And the third thing, as you may have seen here, there is these PIs that we call twists or enhancements to the level structure that also sit around here. If the graph is compact type like here, these MIs are uniquely determined by the genera and the vanishing orders here. But if the graph is not compact type, this is actually an additional datum that you have to record. So up to easy multiplicity, product of the PIs and this cardinality of an automorphism group, that's his relation. Summing over all gamma L and P. And one more thing, you might wonder, this depends on I. Where is the dependence on I here? Well, the dependence is that there is two levels. So the value set of L is 0 or minus 1, say. This has two levels, and I is on lower level. Okay? So most of the, a priori, here most of the points can go anywhere, most of the marked points, but the ith point, like let's say like the first point here, has to go on the lower level vertex.
I'm sorry, what exactly is the class on the right-hand side?
Oh, this is just the class of this divisor class, just that locus. And as you correctly pointed out, I mean this class is plain 0 if the locus of such graphs with such a level structure and that thing does not happen not to be a divisor in the incidence variety compactification. So actually, overall, whenever okay, since my time is now basically up, I can end the story in one sentence and say, you take that relation, you multiply by, okay, let's compare the two. What's the difference between the two? If you multiply by product of all j different from I psi j, and also psi to the, how much, 2g minus 2? Yes? If I multiply that, then if I, then here I get that expression, well, divide by n plus 1, and that gives me this expression. So in order to prove that the right-hand side is equal to 0, is equal, I should show you that when I multiply that class by that expression, I get 0 on the right-hand side. And in order to do that, I would have to dive into understanding those boundary divisors and how you can compute actually such intersection numbers on the boundary divisors. And I can tell you this can be done. Okay, thanks for your attention, at least for the first recursion.
Is there a lattice points version or analog in the instance variety?
I'm not sure if I got the question.
So you said you could compute volumes using the very first method by computing lattice points.
Yes.
So
the incidence variety
are there lattice points analogs in the incidence variety?
The incidence variety compactification is a boundary, so it's complex codimension 1. If you want to do a Lebesgue measure, you don't want to compute there, do you? I'm not sure if I understand what you actually want to do there. And one more warning there. So for, as I said, the mu i's are partition of 2g minus 2. They're positive. They are zeros. Meromorphic differentials, where the mi's are allowed to be negative, are interesting in many respects, and somehow the recursion, the boundary strata, are of those meromorphic types in general. I mean, here you see a little bit, and there could be more meromorphic stuff. In particular, the proof of that formula by Adrien runs through the meromorphic types. So you might be interested in including meromorphic stuff into many pictures, but it doesn't make sense to talk about Masur-Veech volume of meromorphic strata, or at least you'd have to come up with a clever idea of making sense of that, because whenever you have a pole, the volume of the flat surface is infinite. Yeah, I don't know.
Is there an explanation so that only the psi and the psi classes arise in the volume formula?
Well,
I mean, besides
yes,
the proof stuff, but
there should be. I mean, on the psi you can put a metric by using the area form. If you can compute the curvature of the metric and wedge it to that number of times, you get exactly the part that comes from the absolute periods when you do Masur-Veech. So if you're able to put a metric on those bundles, or in fact maybe you should take well, you might also take powers of those bundles, MI powers, but hardly matters. Put a metric there and compute the curvature.
why should you get the relative periods then?
Yeah, that's your trick. You can put zillions of metrics, and the curvature form can take zillions of shapes. For you to, the challenge in order to make really sense of that is get the relative periods, and you're even allowed to get relative periods plus absolute periods junk, because when you have the absolute period junk, wedged with that thing goes away. So, but you should not get relative periods multiplied by some varying function. And you have to do everything as it should be continuous. I mean, happy to work with singular Hermitian metrics, but that also needs justification.
Is there any other geometry problem where you have the same time recursion but a different h function? The variance of that. You should still produce something symmetric in the end.
Yeah, that's a good question. I don't have a direct answer. I'm sort of repeating the question. You can take an arbitrary h function with that maybe that sum condition, I mean the total weight condition that is encircled there, and I would guess the chances are almost zero that the volumes that you define, picking out M1 and M2 or respectively other ones, would be consistent independent of that choice. I haven't tried analyzing what's the constraint for that function in order for that to be true. Although a little bit of it is built into the paper in one of the recursions, but I can't analyze it from that perspective.